Welcome, friends, once again to another episode of DEKB7QHC. I'm Richard Clark, KB7QHC. And in today's episode, we're going to discuss common mode. And it's something that you'll probably have to watch several times because there's some subtleties in this. However, the subtleties are very, very easy to understand as long as you apply them together with all the other, common mode. What does common mode mean? Common mode is for any circuit, a complete circuit loop, has currents that are introduced that are from another source through various forms of linkage, either inductive or capacitive or radiative. Especially radiative in the sense of antennas that are unbalanced often encounter what's called common mode currents. And those common mode currents are definitely in, if you have a Wyndham antenna, that is an offset dipole, the lengths of the two arms, one being shorter, the other being longer, you have an imbalance with respect to ground. Now, one way of solving that imbalance is, make that as long as that. Unfortunately, we don't often have that choice available to us, especially when the terrain does not match our needs for balance. In other words, let's say one end of the dipole is lower than the other. Again, we have an imbalance in ground, even though the arms are equal in length. So, again, the mounting points dictate this problem, introduce this problem, and dictate that the solution be something either raise the short end or snub the currents at where they lead back into the shack here. So let's consider this loop. And I'm going to have a drawing here for you. And in this loop, this is a ferrite bead. That is, the material is made of ferrite, and it's a product of Ferrite, a company that builds these beads for use in many applications, especially for EMI suppression. You'll find them on cables that go to your computer. USB generally have a little barrel at the end of the connector, or behind the connector, and this is a ferrite application. And it's suited to this kind of situation where we have a loop going through the core of this bead. So this is a continuous wire to a load, to a continuous wire back to a source. And well, okay, that's the configuration. What does this bring me? Well, it brings me this resistance here. In other words, we now have a voltage divider between this resistor and this resistor, which was formerly the load. And this resistance appears by virtue of the ferrite material's magnetic properties. And in this regard, the loop goes through and outside the core. This is your first primary lesson in not only common mode but balun construction. This is going to turn into a very simple one-to-one balun in very short time. But however, if we have this loop configuration where one wire goes through the middle and one does not, and those wires meet a load and are driven by a source, this resistance will appear in this lead. Now, however, if we shift the transmission line, such as it is, this can either be coax or twin lead as shown. It's immaterial. And this source, through this transmission line, is connected to this load. We have absolutely no resistance presented to this loop. Now notice that this loop is entirely going through the middle of the bead. This is significantly different from this situation. Notice that I have a resistor introduced by virtue of this being unbalanced. This is unbalanced. This is balanced. Now, so what's the purpose of this bead, Richard, if it's invisible to the currents that are moving along these two lines? Well, we need to introduce Earth. And Earth is always close to us. And you might think, well, where does the problem come from Earth in this regard? Well, straight coupling at both ends introduce these circuit elements, two capacitors, coupling to ground, and ground completing a path between the two. That is outside of this first loop. So we have a larger loop that goes and is broken, well, we'll just move to the next slide. In this regards, we have now resistance, the resistive characteristic of the ferrite is introduced into both leads as resistive elements that create a voltage divider, R, and R to this source, which is to say something is getting, power that's flowing in this direction is getting lost in regards to this load. Now, this is a tricky image in that this coupling and this coupling introduce a current path. I've sort of imaged that before. And that current path is the common mode current. And this is the common mode current that is the point of interest in every discussion of removing it, for one. These resistors impede the flow of this current on both sides of this source. Now, the magic of this is this resistance only appears to this current, the red current, not the blue. The source still sees the resistor, the load, the antenna as it were, a dipole perhaps, as a complete circuit without these resistive elements as part of the blue circuit. The blue circuit is balanced. It's always been balanced in regards to itself, certainly. But when we introduced ground, we had another path. And this path goes through both of these leads equally, so they're snubbed equally. They both see this resistance. This path, however, is balanced in that when this is positive, this is negative, and when this is positive, this is negative. So these resistive elements are never present in this blue circuit. Now, this brings, well, where did this current come from? And I introduced this common mode voltage generator here. It could have been a common mode current source as well. Either way, the question is, what is the source of the common mode? Well, that comes from anywhere, absolutely anywhere. Let me come back to the shack. This common mode voltage comes from the antenna itself. It's coupling to the ground. It has a voltage, a potential difference between the two ends, of course, so we have a flow through the earth on that basis alone. Can't escape that. That's part of the embrace of earth. Now, if the earth and the antenna and the couplings are balanced, there's no problem. However, like I said, sometimes one end of the antenna is lower than the other. The imbalance is going to find its way into the feed line and back into the shack here. If we run that feed line through a bead ferrite, it will introduce a resistance to that current. And if we introduce enough resistance, we're going to diminish that current considerably, irrespective of its source, except as a function of frequency. The ferrites at very low frequencies impose no resistance whatever in any configuration. Any of the drawings that you saw before only work in certain frequencies. And the ferrites, all the ferrites that I'll present you later in another episode, have remarkable characteristics that are overwhelmingly present in the HF band, UHF band, VHF bands, but absolutely nothing of it appears in LF or VLF. So we have VLF at one end, HF at the other. Over here, ferrites present no resistance. Over here, they do. That's one significant point. And again, this goes to Bellin construction, much less EMI suppression. And knowing the frequency issue and the bulk material characteristics that present this resistance in these configurations that I've shown you, you're going to have to look at this several times to pull this together, I know. It's a very simple concept, but it's we come to it with a lot of prejudices of how circuits look like, what they work, and common mode is, you say, well, I've got two wires. I'm going for my tuner. This is I have twin lead. I use twin lead. It's balanced. Maybe. So, what's the source of this common mode? Well, other than the antenna itself, it's other equipment around us that's radiating into radiating everywhere. And it getting into the antenna system, it has to, the coupling, as I've shown before, straight coupling as it were, can be introduced through the masts that you use, can be introduced by the transmission line itself, especially if it's coax. And this is where a lot of problems arise, is in the visualization of a coax as being two wires. It isn't. It's three wires. The coax is unbalanced by definition. When the interior signals of the two-wire system, the inner shield, or the inner surface of the shield, and the wire that's migrating through it concentrically, when we get to the feed point, the little connector, there's also the outer surface of the transmission line, in this case coax. That's the third wire. The coax braid is two surfaces, two wires. That they're physically the same wire doesn't matter. Electrically, they are two different wires, and they act in their own separate circuits. And that extra wire is why we use these sleeve ferrites to snub that current on that third wire. Okay, so I've kind of raised the temperature here as far as the alarm of what common mode currents are, where they might come from, anywhere, but generally from your own antenna. And some of the problems of balance being sometimes is often out of your control. So hence the introduction of ferrites. They solve that quite simply. And we'll discuss how to do that in future episodes. But from here on, I'm just going to wrap it up and say 73, friends. And I hope to see you in those future episodes.